Okay, and go ahead and shoot.
Well, the first one's more of the last module, if I can ask a question about that.
So which one are we talking about? Seven or
The let me pull it up. It's the one with the it's how I know with elements are which elements are arranged and how I, oh my god. It's knowing it's the last module, so it's 7, I think. Are we in 9 or 8 right now? 9. So it's 8. It was 8. It was how would I know the order of elements when they're arranged in increasing ionization energy?
increasing ionization energy?
Yes, because like there was a like in the video you had a question like
Yeah.
which
Can
of
you
these?
see what I'm writing?
No, it's just a white screen still.
Okay.
It's like one of your questions from the videos is like I
Okay.
think 5
Can you
different
see what I've
elements
written
lined
so
up.
far?
Yeah, I can see that.
Okay, great. So ionization energy is often abbreviated IE. And basically it's when you take an atom in the gas phase and you add the ionization energy. And what happens is you take that atom and you turn it into an ion, also in the gas phase, plus an electron, which is in the gas phase. So this is called ionization energy. And I'm going to call this ionization energy 1 because if you have an atom with 2 electrons, you'll have 2 of these, the first and the second. Okay? And if you have 3 electrons on your atom, you'll have 3 of these, the first, the second, and the third, and so forth and so on. Okay, so here, that question is really referring to ionization energy 1. Most of the questions do. They refer to the easiest electron to remove. So when you look at a periodic table, and I'm going to make a very general periodic table, in a period, the ionization energy increases to the right. So in a period, if we were to look at carbon versus nitrogen versus oxygen, in general, we would say carbon has a smaller ionization energy than nitrogen, and nitrogen would have a smaller one than oxygen. So that's the general rule of thumb. And in a group, it goes this way. So when you look at, say, oxygen, sulfur, and let's see, I'm not sure what element is below sulfur. Let me take a look. Selenium. We would say that selenium is less than sulfur is less than oxygen. So this is a general way of looking at the periodic table to decide what has a greater ionization energy. It works for the most part. It doesn't work in some cases, though. So does that kind of answer the question?
Yeah, no, that answers it.
Okay.
And
you said you had another question, I thought.
yeah, I do. It's just a quick one. It's just how, with the Lewis structures, just knowing which element would be in the central part. Just
That's
figuring that
pretty
out.
simple. You can use ionization energy to actually decide. You're going to use the one with the smaller ionization energy.
Oh, all right.
So here, if you had a choice between carbon, nitrogen, and oxygen, you choose carbon. If you had to choose between selenium, sulfur, and oxygen, you choose selenium. So you choose the one with the smaller ionization energy. And the book actually says the central atom, you want to use the one with the smaller electron affinity. Okay. Now, it turns out that if I were to show you the general trend in electron affinities, this is the way it would look. So smaller electron affinity to the left and smaller down. So here, it doesn't matter whether you say choose based on ionization energy or choose based on electron affinity, you come to the same choice.
Oh, all right.
Okay.
That answers that.
That's it.
Yep.
Now, I actually tell you that if you want to choose the central atom, the best thing to do is often choose the one that usually makes the most bonds. The caveat is that sometimes you choose the one that can make most bonds. So sometimes it'll be the one that usually, and sometimes it'll be the one that can. Because when we say that usually they make a certain number of bonds, that's the case. They usually do, but it could change. Some of them can make 2 bonds usually, but they can also make 4 or 6. And so if you have that as one of your choices, you'd probably choose that as your central atom because it can make 6 bonds. And naturally, the central atom is the one that's going to be doing a lot of bonding. So we'll probably see some application of that in a bit.
All right. That was it. Good questions. Thank you.
Okay. Jackie, do you have any questions?
No, I don't have any questions.
Okay, well then let's just get to doing some problems, okay? You do have a quiz coming up on Thursday and an exam coming up on Friday. All right, so I've written out some problems here. And I'm not going to really explain anything from the lectures independent of these problems. I will explain things as we go through these problems. So we want to draw Lewis dot structures for the following. So we're going to start with this A, CS2. And your first step in getting a Lewis structure is to first count valence electrons. And to count valence electrons, you sum the valence electrons of each atom. And then you account for the charge. And when I say account for the charge, if you have no charge, there's no change to the valence electrons. If you have a -1 charge, you have to add a valence electron because that's how you get the negative charge. If you have a positive charge, you have to remove or subtract a valence electron because that's how you get the positive charge. You take an electron away. So in the case of the CS2, you have a carbon plus a sulfur plus a sulfur, which means you have 4 valence electrons for carbon because it's in group 4A, 6 for sulfur because it's in group 6A, and 6 for the other sulfur because it's in group 6A, for a total of 16 valence electrons. The second thing you do is you pick the central atom. And here, carbon tends to make 4 bonds and sulfur tends to make 2 bonds. And the reason you know this is because carbon has 4 valence electrons because it's in group 4A, and sulfur has 6 valence electrons because it's in 6A. And this is often how you draw their, what's they're called their Lewis dot symbol. And if you want to know how many bonds they tend to make, you just count the number of single electrons. So 4 bonds. How many single electrons in the sulfur? Well, this is a pair, and this is a pair. So there's 1 single and 2 singles. So sulfur tends to make 2 bonds. So between the two, which one are you going to choose? You're going to choose carbon. So the second thing you do after you count valence electrons is you pick your central atom. And you're going to, whoops, I don't know where the hydrogen came from. Pick your central atom and you attach the surrounding atoms to the central atom. And then what you need to do is you need to put lone pairs on the surrounding atoms, like so. So that's called a lone pair. The reason it's called a pair is because there's 2 of them. The reason it's called lone is because it's attached to a single atom, a lone atom. So these are not bonding electrons. You would call them non-bonding electrons. So there's one of your sulfurs. And you keep adding lone pairs until you get 8 around your sulfur, 2, 4, 6, 8. Remember, a bond has 2 electrons. So that counts as 2, 2, 4, 6, 8. So here's what we end up getting when we use or put octets around these surrounding atoms. Now, if I have any more electrons to use, I'm going to dump the rest of them on carbon. But if we count how many electrons we've used here, we've used 8 here and 8 here for a total of 16. So I don't have any more electrons. So in some cases, this is going to be okay. Some atoms don't need to have an octet. Carbon is not one of those. So how do you get an octet on carbon? And the answer is you could do a number of things, but they all involve taking a lone pair and making them a bond. So one of the ways we could get a Lewis structure that would work would be to take our sulfur and take two lone pairs and turn them into bonds. So when you take a lone pair and turn it into a bond, two dots make a line. So you can see above here, I've taken two dots and made a bond, and two dots and made a bond, and two dots I've left alone. And the reason for that is because when I make these two extra bonds to carbon, this carbon now ends up with 8 valence electrons. 2 for each bond. 4 bonds times 2 is 8. So this carbon now has an octet, and that's kind of our driving guideline for Lewis structures, is to get an octet, but we break that rule a bit. So here we look at that Lewis structure. We could also have done the same with the other sulfur. So this is another way to do it, but we could have also done this. We could have taken a double, a pair of electrons from this sulfur and made a double bond. And we could have done the same with the other sulfur. So these are the 3 possible Lewis structures for CS2. One is better than the others. And one way to evaluate the Lewis structures is ask yourself, do all of the atoms have the bonds that they usually make? Because if they do, that's a pretty darn good Lewis structure. So do any of these have the bonds? Do all the atoms have the bonds they normally or usually make? And it's this one here. Carbon normally makes 4 bonds, and there's a carbon with 4 bonds. Sulfur usually makes 2 bonds. There's a sulfur with 2 bonds, and there's a sulfur with 2 bonds. So we really like this just based on the number of bonds they normally make. This one, the sulfur has 1 bond, so we don't like that so much. This one, the sulfur has 3 bonds, so we don't like that so much, and same for over here. So these are not as important. There's another way to evaluate these 3 choices, and that's using formal charge. And that was not the question here, but I'm going to introduce the idea to you. So formal charge is a simple idea. So I'm going to draw one of those structures that we got that we said, you know, we don't like it so much. And formal charge is based on the idea that you're going to split this thing up into its individual atoms. And when you split it up, each atom gets to keep its non-bonding electrons, and each atom keeps half of the bonding electrons. So between this sulfur and this carbon, there are 6 shared electrons. The sulfur would keep 3. And the carbon would keep 3. Now on this side, the carbon would keep 1 of the shared electrons, and sulfur would keep 1. So I'm going to ask for a thumbs up if you understand how I split these up. Okay, good. Now to assign formal charge, here's what we know. Based on the periodic table, the carbon in 4A should have 4 valence electrons. Okay. How many valence electrons does this carbon have? It has 4. Now this is a neutral carbon atom, and this with 4 valence electrons is a neutral carbon atom, so its formal charge is 0. Now nitrogen is here with 5 valence electrons. Oxygen is here with 6 valence electrons, and sulfur is here with 6 valence electrons. So a neutral sulfur atom has 6 valence electrons. This one has 7. What's going to happen to the charge on a neutral carbon atom if you gain an electron? And the answer is it will have a negative charge. So the formal charge on this sulfur is a -1. And then lastly, if we look at this other sulfur, do you see how it has 5 valence electrons? If it's neutral, it's going to have 6. What happens to the charge if you take one away? Well, it becomes positive 1. Okay, so when we look at this guy here, the formal charges are as follows. -1, 0, and +1. For the other structure we had the single bond on this side and the triple bond on this side. And the formal charges are -1, 0, and +1. Now for this one right here, I want you to assign formal charges to each atom. And once you're done, give me a thumbs up so that we can talk about it. Okay, so if you split these up, you should have gotten something like this. There's your sulfur. There's your carbon. And there's your sulfur. Notice when I split these up, if they're shared electrons, I kind of put them on the side of the atom that was bonded to the other atom. So if you look at this carbon compared to this carbon, this has 4 electrons, this has 4 electrons, its formal charge is 0. This sulfur has 6 valence electrons, this has 6, its formal charge is 0, and this one, the formal charge is 0. A really interesting thing, if you add up all the formal charges, when you add up all the formal charges, 0, 0, 0, it equals the charge on the molecule. So how do we evaluate these based on formal charges? Well, for formal charges, the best structure is going to have all formal charges equal to 0. Now, sometimes you have to have a formal charge on one of the atoms. So if you do have a formal charge, you want formal charges to be +1 or -1, but nothing else. You don't want 2s or 3s or -2s or -3s or anything like that. So you want the formal charges to be +1 or -1. And if it's a -1, you want it to be on an electronegative atom, if possible. And if it's on +1, you want it to be on the less electronegative atom. So that's another way to evaluate this structure here, is we can evaluate it based on formal charges. The more zeros you have, the better. And what that means here about formal charges is this idea. If you do have formal charges, it means the electrons are not distributed evenly. If you do have 0 formal charges, the electrons are distributed evenly. And these valence electrons repel one another because they're negatively charged. So let's take a look at another problem now. So let's look at this Bf4-. Okay, so you've got a boron plus 4 fluorines, and then we have to add a valence electron for the negative charge. Boron has 3 valence electrons, fluorine has 7. So when you add these all up together, you get 32 electrons. Now, which atom are you going to put in the middle? Boron usually makes 3 bonds, but it can also make 4, it turns out. And the reason we say it usually makes 3 bonds is because it has 3 singles. Fluorine, with its 7 valence electrons, has 1 single, so it makes 1 bond. So naturally, we're going to put boron in the middle. And we're going to do this. Now, we put lone pairs around each fluorine until you get an octet, 2, 4, 6, 8. So to get an octet, the fluorines already have 2 electrons. We add 6 more. And you do this one fluorine at a time. Okay, and here you'll find out we've used all 32 electrons. And finally, we do this to let people know that we're getting the Lewis structure of an ion. You use bracket and the charge on the outside of the bracket. So this is your Lewis structure of this BF4. And if we assign formal charges, I'm going to show you another way to get the formal charge. You take the number of valence electrons in the neutral atom, and you subtract from that the non-bonding electrons. And you also subtract from that 1/2 of the bonding electrons. So this is if you want to have a formula for getting this. The way the book puts this is you have NVE, the number of valence electrons, and then what they do with this is they do this, NBE, non-bonding electrons, and then plus 1/2 of the bonding electrons. So they kind of combine these two together and take the negative on the outside. This is what they have for the formula. So if we want to get the formal charge of a fluorine that has 6 non-bonding electrons and 1 bond, this is the way the formula would look. Fluorine has 7 valence electrons. How many non-bonding electrons? 6. How many bonding electrons? 2. So this ends up being 7 minus 6 plus 1, which we can see ends up being 0. So the formal charge on this fluorine is 0. What is the formal charge on this fluorine? Well, it's the same thing. It's got 3 non-bonding or 6 non-bonding electrons. It's got 2 bonding, so it's going to be the same. So if all of these are zeros, what does the charge on the boron have to be for the formal charge? And the answer is -1, because all these formal charges have to equal that. And if we do the formal charge on that boron, it's going to equal, so boron is has an atomic number of 5, but it's in group 3A, which means it has 3 valence electrons, minus the non-bonding electrons are 0, and then plus 1/2 of the bonding electrons, which are 8. So you get 3 minus 4, which is -1. So any questions about this Lewis structure and the formal charges? If you're okay with that, give me the thumbs up. Okay. Then let's try another one here. So we're going to do this molecule here. This is nitric acid. Now, for this one here, this is based on NO3 -1, and this is the nitrate ion. And when you add a hydrogen to it, you get HNO3. So nitric acid. Now, to help us decide how this thing is going to be made, we're actually going to do NO3 and not HNO3. So for NO3, how many electrons do we have? We have 5 plus 18 plus 1. So I'm kind of jumping out ahead here. Instead of writing everything out, we've already done that a few times. There's 5 valence electrons per nitrogen because it's in group 5A. There's 6 per oxygen, and with 3 oxygens, that's 18. And then the -1 is another valence electron. When we add this all together, we get 24 electrons. Now, which of these atoms are we going to put in the center? And the answer is the nitrogen. because it tends to make 3 bonds. So that's what you get. Okay, now we've used all 24 electrons and the nitrogen does not have an octet. So what we're going to do is we're going to take a lone pair and make it into a bond. And now the nitrogen has an octet. We're going to put a minus on the outside, and we're going to assign formal charges: -1, -1, 0, and +1. This has a lot of formal charges that are zeros. So you might ask, why not do this? So you can see here, I've made double bonds to each oxygen. So this is a 0, this is a 0, this is a 0. And then this would end up being a -1 on the nitrogen. And the reason we don't do this is because nitrogen can only make 4 bonds, and that's it. Anything in period 2 can make a maximum of 4 bonds. So this is no good. You need to be in period 3 or 4 or 5 or bigger to be able to make 6 bonds. So this is not possible for this guy. The maximum we can get are 4 bonds. So this is what we have to live with for this particular structure. Now, let's look at this H+. What does its Lewis structure look like? Well, here is a neutral hydrogen atom. And here is an H+ atom. It has no valence electrons. So what can happen here is this guy with no valence electrons can react with this guy here. And this is what's going to happen. We have to think about, where's this hydrogen going to attach? Because it needs a pair of electrons to attach to. Is it going to attach to those electrons, those? Basically, our choice is, will the hydrogen attach to one of these 2 oxygens or this guy? And the answer that makes the most sense is this. It's going to attach to one of these oxygens through a lone pair, making a bond. And the reason we think it's going to do that is because that oxygen now has the number of bonds that it would normally make. And now when we look at the formal charges, we've got a 0, a 0, a 0, a -1, and a +1. So it's actually improved the number of zeros when we add that hydrogen. So this is excuse me, not the resonance. This is the Lewis structure for nitric acid. So this guy here is one of these things that's called an oxyanion, or sometimes an oxoanion. And with these oxoanions, you have some atom in the middle and you have oxygen surrounding them. So what are other examples of these oxoanions? Well, let me show you some more oxoanions where you have some atoms surrounded by carbons. So here are different examples of these oxoanions. You could actually consider OH minus to be an oxyanion, but there's NO3 -1, CO3 -2, SO4 -2, PO4 -3. So what is the central atom for each of these? Here, the question is moot. When you don't have 3 atoms, you don't have a central atom. When you have 3 or more, you have a central. What's the central atom here? Nitrogen, carbon, sulfur, phosphorus. So each of these are going to look like this to begin with, before we start filling in the electrons. Okay, so those are those oxoanions, and that's how, for these oxoanions, if you add a hydrogen to any of these, you always add it to an oxygen. Okay, so are you okay with the Lewis structure for this? Oh, shoot, I did the wrong thing. I did HNO3. Let's do HNO2, but now we know a little bit better. It's HONO. I did the wrong thing, but that's all right. So let's do this HNO2. And you guys are going to help me out now. So for this HNO2, what are we going to choose as the central atom? Hydrogen. If you think it's hydrogen, give me a thumbs up. Nitrogen, give me a thumbs up. Okay, nitrogen is it. And we're going to put the two oxygens here. And where are we going to put the hydrogen? Are we going to put it on an oxygen? If you think that's the case, give me a thumbs up. Or we're going to put it on the nitrogen because the nitrogen's central. So yes would be nitrogen. No would be oxygen. So the question is, do we put the hydrogen on nitrogen? Yes or no? No. Good. We're going to put it here. I always like to put it on the oxygen to the left. That's just my preference. Let's talk about how many valence electrons we have. 1 for the hydrogen, 5 for the nitrogen, and 12 for the two oxygens, for a total of 18 electrons. So once we've done this, we start putting lone pairs on the surrounding atoms. So here, 1, 2, 3, 4, 5, 6. And now we have 8 on that carb or oxygen, excuse me. Here, 1, 2, 3, 4. And now we have 8 on that. 8 and an 8 stands for, or totals for 16 electrons. And now we have 2 more to put on here. Where do we put the remaining valence electrons? Right on the central atom as a lone pair. Okay, now let's take a look here. Do we have an octet on the oxygen? And the answer is yeah. Do we have an octet on hydrogen? And the answer is no, but it's not supposed to have an octet. It only gets a duet. So it does have a duet. Is there an octet on nitrogen? No, there's only 6. So how do we get an octet on this nitrogen? We have 2 choices. Here's one choice. Make a double bond to the nitrogen to the oxygen on the left. So that's one choice. I'm going to call that 1. The second choice is make a double bond to the oxygen on the right. Okay, what I want you to do with these 2 structures is I want you to assign formal charges to each atom and decide which one is better, which resonance structure is better. I just threw a word at you called resonance structures. When you have 2 possibilities, they're called resonance structures. And to evaluate them, you will usually use formal charges. Once you've looked at the formal charges and evaluated, give me a thumbs up. Okay, so I'm going to show you the formal charges. There's a 0 on this hydrogen. There's a 0 on this nitrogen. And for this oxygen, it's got 1, 2, 3, 4, 5, 6. It's got 7 electrons formally. It should have 6 to be neutral, so that's a -1. And since this molecule is neutral, this has to be a +1. Here, the hydrogen is 0, the oxygen is 0, the nitrogen is 0, the oxygen is 0. And the reason I'm good at assigning these formal charges is because I'm not actually using the, I'm not using this. I'm actually not using this formula. I'm using the fact that that oxygen has 2 bonds, which it usually makes, and that means its formal charge is probably 0. This nitrogen has 3 bonds, which is what it normally makes, so the formal charge is 0. This oxygen has 2 bonds, which it normally makes, so the formal charge is 0. This one, in fact, looks just like the oxygen we would draw if it were a pure neutral nitrogen or oxygen atom. This hydrogen usually makes 1 bond, formal charge is 0. So based on the formal charges, this is by far the best. And we say, no thanks. Okay, so this is the correct Lewis structure. All right. So that's this HONO, if you will. It's another one of those oxoanion or oxy acids. So this is an oxy acid. All right, let's try another one now. Let's try this OSCl2, and the sulfur is in the middle. I want you to go ahead and see if you can come up with the Lewis structure. When you think you've come up with the Lewis structure, let me know. So when do you think on these little choices where they have yes, no, go slower, go faster, and more, when are they going to put this one up there? Like cowabunga? Never? Okay, you guys are done. So I counted 26 electrons. Sulfur is going to be in the middle, and I like to make it look symmetrical. So I put the oxygen going up and the 2 chlorines to the left and to the right. So the chlorines have octets, the oxygen has octets, and we've used 24 electrons. That means we have 2 left over. Where do they go? They go on sulfur. So we could be done with it and say, hey, we're done. Let's assign formal charges here. The chlorines are 0. The oxygen is -1 and the sulfur is +1. So is this the best structure? And it turns out, I think it's not. My mistake, I've moved the oxygen and I don't want to do that. So I'm going to leave the chlorines as they are because they have the number of bonds they normally make. I'm wondering, can I make a double bond with this oxygen by taking this lone pair and making a bond out of it? So we get this guy here. These guys are called resonance structures. I want you to evaluate formal charges on this second drawing that I've made. And when you've found out the formal charges, let me know by giving me an okay. Okay, so I'm going to figure out the formal charge on sulfur here. Sulfur is in group 6A, so it has 6 valence electrons. The number of non-bonding electrons are 2. And the number of bonding electrons are 8. So half of 8 is 4, plus 2 is 6, 6 minus 6 is 0. So here, the formal charges on each one of these is 0. So based on formal charges, which structure is better? This one's better, and this one is not better. So this is what I'd like to see on your exam, is the second one. Now here, the sulfur is a hypervalent atom in this case. Hypervalent meaning that it has more than an octet. So what elements can have more than an octet? And the answer is really simple. Anything beyond period 2. I'll repeat that. Any element beyond period 2 can be hypervalent and have more than an octet. Anything up to period 2 can have at a maximum an octet. That's it, a maximum of an octet. Beyond period 2, they can be hypervalent. Will they always be hypervalent? No, but they can be. So we're done here. Any questions about this molecule here? Okay, we're going to move on then. So this is just more and more practice of drawing Lewis structures. So let's take a look here at this chloro-difluoromethane. So how are we going to interpret this? So I'm going to write the formula down. Not the name, but the formula, because that's what we're going to use to draw the Lewis structure. And the formula is given as CH ClF2. I think this is used as a refrigerant. Okay, so which atom are we going to put in the middle? Carbon. So to make this look somewhat symmetrical, I'm going to put the fluorines on the left and the right, the hydrogen up, and the chlorine down. You don't have to do this. If you want to make it all jumbled, that's fine. Heck, if you wanted to do this, and make it look more like a times than a plus, that's fine also. Let's count electrons. 6 for the carbon. Oop, my bad. 4 for the carbon, 1 for the hydrogen, 7 for the chlorine, and 14 for the 2 fluorines, which comes out to 26 electrons. Okay, so let's put the electrons in. Lone pairs on the fluorines. Notice we never put lone pairs on the hydrogen because hydrogen makes 1 bond and that's it. Lone pairs on the fluorine, lone pairs on the chlorine until we get the octet, and we have 26 electrons. And if you assign formal charges, you get a 0 here, 0 here, 0 here, 0 here, and a 0 here. This one doesn't get any better than that. If you're okay with this one, give me a thumbs up. Okay, let's do this next one here. Propanoic acid, which has this formula. And thank goodness they tell us this is what it looks like without all of the lone pairs and so forth added to it. So let's see what that looks like. So this is what's given. Okay, and let's figure out how many electrons this should have. We have 3 carbons. We have 1, 2, 3, 4, 5, 6 hydrogens. And we have 2 oxygens. From the carbons have 4 valence electrons each, so that's 12. The hydrogens have 1 each, so that's 6. The oxygens have 6 each, so that's 12. When we add this all up together, we get 30 electrons. So let's see how many we've used so far. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We've used 20 electrons. We have, did I count that right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And we just have to add the rest in. So we've got 20, let's add the rest in. So I'm gonna put 2 here and 2 here. So now we're at 24 electrons and we have 6 more, and I'm gonna do this. And we've used our 30 electrons. So let's evaluate this. Remember, if it's in period 2, we'd like for them to have octets unless it's boron. So here, carbon has an octet, 2, 4, 6, 8. This carbon has an octet, 2, 4, 6, 8. This carbon does not have an octet. So how do we get an octet? We have to take a lone pair from a neighbor atom and make it a bond. We have 2 choices here. Now, let me ask you this. Without drawing both choices, is it clear which oxygen we're going to take the lone pair from and make a bond? So this is a yes, no. Is it clear which oxygen is going to make the double bond to carbon? I got 1 yes. Okay, so is your reason simply this, that by making a double bond to that oxygen, you get the number of bonds that oxygen normally makes? Is that how you picked it? Yes? Or you could say, if I made a double bond to the wrong oxygen, it would have 3 bonds, and that's why I did not pick that one. So it's pretty clear what you're going to do here, in my opinion, is this. Now, which one do we turn into the double bond? It doesn't matter. I like to make it look symmetrical, so I take the top 2 and I make it into the double bond. And by the way, when we have 2 parallel lines with 4 shared electrons, it's called a double bond. When it has just 2 electrons in a single line, it's called a single bond. So single bond, double bond, and then there are triple bonds. All right, if you guys are okay with the Lewis structure for this propionic acid, give me a thumbs up. Are you okay, Jackie? Okay. So let's move along. And now we want to do this acetonitrile, which is CH3CN, and they give us this. So CH3CN, and they give us this. So what they're trying to tell us is that a carbon is bonded to a carbon is bonded to a nitrogen. Now, I'll tell you, we've already seen that carbon likes to make 4 bonds. And you know hydrogen makes single bonds. So when you see something like this, you know this is wrong. Why do we know this is wrong? And the answer is that hydrogen has 2 bonds. Hydrogen only makes 1 bond. So this clearly has to be wrong. So what does something like this mean? Well, it means the carbon is going to have 3 hydrogens bonded to it. And then what is the other bond for a carbon? It's to this next atom here. And then the nitrogen. So this is the initial structure. If we count electrons, we have 4 for the carbon, 3 for the 3 hydrogens, 4 for this carbon, and 5 for the nitrogen, for a total of 16 electrons. Okay, so far we've used 2, 4, 6, 8, 10, 12, 14, 16. So the idea here is that when you're trying to put lone pairs on these surrounding atoms, you keep going until you get an octet. You don't try to be fair and say, well, I'm going to put 2 here and then 2 here and then 2 here. Don't do that. You put the lone pairs on the surrounding atom until it has an octet before you even think about the middle atom. So this is a middle atom, this is a middle atom, but this middle atom's good. But you put the lone pairs on the surrounding atom. All right. Now let's evaluate. We want carbon to always have an octet. Does it have an octet here? No. So how do we make an octet? We're going to take these two and make a bond, and these two and make a bond, and this now becomes this. Now, does this nitrogen have an octet? Let's find out. 2, 4, 6, 8. Indeed, it does. Does this carbon have an octet? 2, 4, 6, 8. You bet your bippy. Does this carbon have an octet? 2, 4, 6, 8. You bet your bippy. Does this hydrogen have a duet? 2. Yep. Does this hydrogen have a duet? Yep. 2. And does this hydrogen have a duet? Yep. 2. And there you go. All right. Now, why do we say that these form a duet and these form an octet? Well, because this hydrogen here, if I redraw this, what's going on here is this hydrogen is thinking. So this is my little think bubble. You guys ever seen those things where this is your little think bubble? This hydrogen here is thinking, look at me. I've got 2 valence electrons just like helium, which means I'm noble. Everyone wants to be noble. This carbon, it's thinking, well, geez, I've got a total of 8 valence electrons around me, which means I look like neon. I'm noble. What's this nitrogen thinking? It's thinking it also looks like neon. So these Lewis structures are based on the idea that the atoms would like to have 8 valence electrons or 2 valence electrons because they look like a noble gas atom. And that more importantly than looking like a noble gas atom is that they kind of behave like a noble gas atom. And what I mean by behave like a noble gas atom is noble gas atoms are unreactive. So if these have an octet and they're like a noble gas, they're going to be less reactive than if they don't have an octet. Now, why do I say less reactive rather than not reactive? And the reason I say not reactive is because, you know what? They're not noble gases. You can slap as much makeup on them as you want, but they're not noble gases. They might look really good like a noble gas, but they never, ever will be as unreactive as a noble gas. They're not the real thing. Is that clear? So that's why we like octets. Now, which are the atoms that can have more than an octet? The answer is those above period 2. So that means period 3, 4, 5, 6, 7. Okay. Let's do this last one, this allene. This is a very interesting one. So allene, they give C2 or H2C, C, C, H2. So based on the way this is drawn, you know they want you to do this. And what do they want you to do with these hydrogens? Well, they're going to go like that on the end carbons. So count valence electrons, and when you get them, give me the thumbs up. Okay, I get 2 plus 4 plus 4, plus 4, plus 2, for a total of 16 electrons. Oh, is that right? Yeah, 16 electrons. Okay, now so far we have used 2, 4, 6, 8, 10, 12. So what do we do now to get 16? We put 2 here because this is your central atom. So we put on the surrounding atom lone pairs until we get to our octet, and now we're done. Let's evaluate this. Does every atom have an octet? This is a yes or no question. Does every atom have its octet or duet that it would like? Yes or no? Okay, the answer is no. This carbon only has 4 electrons, 2, 4. So how do we get its octet? We take these electrons and make a bond, take these electrons and make a bond, and this is what we get. And there you go. In this structure, does each atom have its octet or duet if it's a hydrogen? That's a yes or no. Right. This carbon does 2, 4, 6, 8. This carbon does 2, 4, 6, 8. So what's really interesting is when we talk about the octet rule here, you get to count shared electrons twice. Okay, so that's all of these. Let's do some more. We're going to speed up our rate at which we go through these now. And when I say speed up the rate, maybe we're going to slow down. So I want you to draw a Lewis structure for methanol. See if you can draw the Lewis structure for methanol. When you're done, give me a thumbs up. Okay, I'm waiting for you guys to come up with the Lewis structure and give me a thumbs up when you've got it. Okay, so let's take a look. You should be used to this now. CH3 is going to be that. So how is this OH going to look? It's going to look like that. And naturally, you expect there to be lone pairs on the oxygen because it normally makes 2 bonds. And without even counting valence electrons, we think this might be a good one for it. Let's count valence electrons. 4 plus 3 plus 6 plus 1 for a total of 7, 13, 14 electrons. Let's count how many we have here. 2, 4, 6, 8, 10, 12, 14. Boom, we're done. Okay, so the next one I have is for us to do is this 2C, what looks like a double bond there, CHCl. Try and get the Lewis structure for this guy. And when you're done, give me a thumbs up. Okay, so I think this first part is going to be a carbon with 2 hydrogens on it and a double bond to that carbon. This carbon is going to have a hydrogen on it and a chlorine on it. And that makes more sense than putting a hydrogen in between the carbon and the chlorine. So this is the start. And if we count electrons, we've got 2 plus 4 plus 4 plus 1 plus 7. So that's 10, 18 electrons. Here we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, and there's the Lewis structure. How about this one here? H2C, what looks like a double bond, CH, CN. Give that one a try. And when you're done, when you think you've got it, give me the thumbs up. Okay, so this is going to be just like the one above, only this time instead of drawing the hydrogen one up and one down, I'm going to draw one up and one to the left. Now here, this hydrogen, I'm going to draw it going up just like I did over here. And that carbon, I'm going to draw over here to the right instead of down. Now, can I attach the nitrogen to this carbon? The answer is no, because I already have 4 bonds to it. So that means I'm going to have to do this. Now, when we start putting electrons in, we find out that we have 2 plus 4 plus 4 plus 1 plus 4 plus 5. So that's 10, 11, 14 or 15 and 20. So we've got 20 electrons. And here we use 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now, why do I put them on the nitrogen instead of the carbon here when this carbon does not have an octet? And the answer is, when you're putting lone pairs onto these things, you always put them on the surrounding atoms first before you put them on the central atoms. So this is what we have to go for. And to make an octet on this carbon, we're going to have to take 2 of these and make a bond, and another 2 of these and make a bond. And we end up with this. And every atom has its octet. Now, if we go back and assign formal charges to each of these, and that's something I want you to do when you're looking at this after we're done, all formal charges are 0 in this. All formal charges are 0 in this, and all formal charges are 0 here. So these are really great Lewis structures because all the formal charges are 0. They have the number of bonds they normally make. These are beautiful. Okay. Now, do you still have time for one more? If you do, give me a yes. Harry, you don't? All right. Well, we'll hold off then because the thing I'm going to cover next are resonance structures. And you do want to take a look at that because we're going to start off with a problem with a nitrate ion, which we already did, but we want to draw resonance structures for it. Okay. So we'll pick up here from here on Wednesday, and we'll basically cover the rest of the chapter on Wednesday, and your quiz will be on Thursday. Most of this chapter should be review. So on Wednesday, not only are we going to do resonance structures, but we're going to do molecular polarity and molecular geometry. Okay. Turn your mics on, say goodbye.
Bye, everyone.
I'll try and post this within the next couple of hours. Okay.
All right. We'll see you Wednesday then.
All right. See you Wednesday. Bye-bye.
Bye.